So we can only talk for about 1 hour before this runs out. Okay, so I thought I would talk about a lot of fun properties of the Fibonacci's. Again, I'm trying to start with something you can do with kids at a very young age and go all the way up to college if you want, just so that this is still tax deductible and valid use of my money. This is the Fibonacci quilt. And so we'll talk a little bit about this. Anybody know what this is made out of?
Yes.
Yeah, and it is?
Little beads of iron.
Yes, fuse beads. And so my daughter and I did most of this. Kim did a little bit, but it was mostly Kayla and myself. Ideally, this should be curving and it should not be straight, but we decided rather than trying to approximate, we would just do straight lines. There's a lot of beautiful mathematics, including a very non-trivial theorem about the Fibonacci numbers that most of you may not have seen. And so eventually I will show what theorem is lurking here. I will show how Fibonacci numbers can be used as a base, as an alternative to base 10 and all these other bases we've been talking about. I will show how Fibonacci numbers can be used to explain why you should not go to Las Vegas and play roulette. And then, if time permits, I'll talk about some of the other fun properties of the Fibonacci numbers. To me, one of the most important things about the Fibonacci numbers is they come from a difference equation. And it turns out difference equations are discrete versions of differential equations. And we can use differential equations to model how the world changes. We can use difference equations similarly. The big difference between difference and differential is continuous evolution. Differential is at time steps. So you might have seen the Fibonacci numbers to be used to model how many rabbits you will have at a given amount of time in the ideal world when there are no predators for the rabbits. And you can then tweak it and you get like the Volterra predator-prey equations, or Lotka-Volterra predator-prey equations, where you now have rabbits and wolves, or as one of my colleagues does, zombies and humans, and try to see how they evolve and what's going to happen as you add different factors.
Rabbits can't turn into wolves.
Rabbits cannot turn into wolves that we know of. And so one of the big things that is going to happen is slightly different notation for the Fibonacci numbers will lead to slightly better algebra. And this is hopefully something you've recognized a couple of times already throughout the 2 classes, that depending on how you look at things, you can make your life a little bit easier. And I want to talk a little bit more about how we can write things in slightly different ways to help really elucidate the structure that goes on. How are the Fibonacci numbers defined? The sum of the previous 2. Does anybody know any other definition for the Fibonacci's? So it turns out there is another definition. Not from this one directly. I'm actually working on a new sequence related to the Fibonacci numbers related to this graphic.
Like the diagonal?
More like something similar to that. But there is another well, you could use the explicit form, but no one would ever define the Fibonacci numbers that way. So the Fibonacci numbers, usually it's Fn is Fn minus 1 plus Fn minus 2, and you have to give me 2 starting numbers, say F0 and F1. And once I know the 2 starting numbers, I can then get everything from that point onward. The most natural candidates for starting is 0, 1. Sometimes people also do 1, 2. And there are advantages and disadvantages to each. So if I do 0, 1, the next one is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, ... If I do 1, 2, I get 3, 5, 8, 13. And so the only difference really between these is a slight shift of index. And in this one, I actually have 2 1s. In this one, I only have 1 1. For some of the stuff I care about, this is actually more convenient, even though this is the more standard one. Is it hard to calculate Fibonacci numbers? Okay, so, but if I give you any 2 Fibonacci numbers, you can get the next one. So this is something elementary school kids, if they know how to add, they can continue the sequence. They may not want to continue the sequence beyond a certain point, but they could continue it. One of the problems is the computational cost of calculating the different terms. To go to the 100th, the 1000th, the millionth, it's very time consuming. You have to get all the stuff in between. Well, it turns out that no, you can actually jump ahead. And so I'm going to show you one of my favorite formulas in all of mathematics. It's called Benet's formula that allows you to jump to any term of the Fibonacci's without computing all the previous ones. For now, I'm not going to say why we care about the Fibonacci's. I'm going to just start off with, here are some fun properties of the Fibonacci numbers, and then we'll do applications later. And I'm still just trying to see, it's almost uploaded. That's how long it's taking. All right, so let's use, this is our definition. One of the things I'm very big on is trying to get a rough sense of size. So we know Fn is Fn minus 1 plus Fn minus 2. So the sequence is basically increasing, especially if I start off with 1, 2, 3. Let's do this one as my sequence. The question is, how fast is it increasing? So does anybody know roughly how big the nth Fibonacci number is?
Almost twice the previous one.
It's almost twice the previous. So it's about the golden mean to the nth. But one of the things we can do is it's less than or equal to Fn minus 1 plus Fn minus 1, which is 2 Fn minus 1. Similarly, it's at least as large as Fn minus 2 plus Fn minus 2, which is 2 Fn minus 2. So by doing like this, I can get a quick sense of how quickly this series grows without doing a huge amount of detailed analysis. So if I do it this way, every time I increase the index by 1, my Fibonacci number at most doubles. So from this part, I get Fn is going to be growing slower than 2 to the n. Or maybe there's a constant in front of it, but defining things as 1, I should be okay. And the reason is, every time I increase my index by 1, Fn is less than or equal to twice Fn minus 1. If I look at the other way, every time I increase my index by 2, I at least double. So that means if I go just 1, it should be about a square root of 2. And so with a little bit of work, you can show in the other direction, it should be at least square root of 2 to the n. So we have some rough sense of how quickly it grows. It's going to be like 1.414 to the n is less than or equal to f to the n is less than or equal to 2 to the n. The actual answer is Fn is about some constant times 1.6 to the n. And that's going to be the golden mean. So what I want to do is I want to show you how we can get an exact formula for Fn. But what I love about this is that without doing a huge detailed calculation, we can still get a rough idea of how it's growing, some rough order of magnitude. Okay. So the way we solve this is one of my favorite methods in mathematics. It's called the method of divine inspiration. So the way the method of divine inspiration works is you just go like this for a little bit, and then you write down the answer. And it's, well, yes, if you're divinely inspired, and there's no need to show your work. And so now, just to make things a little bit nice, I'm going to go with 0, 1, 1. And you get Fn is 1 over square root of 5, 1 plus root 5, it's a horrible 5, 1 plus square root of 5 over 2 to the n, minus 1 over square root of 5, 1 minus root 5 over 2 to the n. And this is called Benet's formula. And it turns out something like this holds for more general recurrences. As long as I have a fixed depth here, and as long as I have integer coefficients, I will always have an expression like this. How do I know this works? Well, if I take n equals 0, I get 1 over root 5 minus 1 over root 5 is 0. If I take n equals 1, okay, the minus means the 1 and the 1 cancel. The root 5's reinforced. I get 2 root 5 over 2, which is root 5. Divided by root 5 is 1. So when n equals 0 and n equals 1, I get the first two terms correctly. Now all I have to do is show that this sequence satisfies the recurrence relation. And then since they agree on the first two terms, and they have the same recurrence, the first two terms specify everything. This is a completely unenlightening proof. It's correct.
How does somebody come up with something?
You don't.
Benet.
Divine.
Yeah, beneath.
No. You have another way, and then you just hide that, and then you just present this. And when you do that, then it looks magical. What can you tell me about the Fibonacci numbers? What kind of numbers are they? Integers. So the way I like to phrase it to my students is, imagine, a number has committed a crime, and we have a police lineup. and you have somebody who's coming in trying to identify the culprit, and you know that the culprit was an integer. There's part of that gang, the gang of integers, okay? If you saw this, yes, that's the integer that did this to me. Does this look like an integer? No, not even close. We've got square roots of 5, we've got divisions by 2, right? This does not look like an integer, but it is. So a nice exercise is, what can I replace the 5s and 2s by so that it's always an integer? If you've taught Fibonacci numbers before, here's a nice tweak to give students. When will you always get an integer? What can you put for 5? What can you put for 2? And so there's a lot of great stuff about why this is an integer. Right. I want to show where the formula comes from. So we have the recurrence fn is fn minus 1 plus fn minus 2. It turns out that this is what's called a linear recurrence. If you have a solution, if I multiply the solution by 5, is it still a solution? Yeah, so if I multiply fn by 5, this is multiplied by 5, this is multiplied by 5, this is multiplied by 5, the equation still holds. So if an solves an equals an minus 1 plus an minus 2, so does bn equals 5 times an. And of course, I don't have to use 5. I could use 51. I could use 511. I could use 1,000. I can do any constant there. That's the first property about this linear relation. If I have a solution, I can multiply it by a constant, and it's still a solution. The next thing is if I have 2 solutions, I can add them, and it's still a solution. So if an solves, and bn solves, bn equals bn minus 1 plus bn minus 2, cn equals an plus bn, also solves the relation cn equals cn minus 1 plus cn minus 2. And in fact, more generally, I can put any constants I want in front here. I could put a big constant a big constant b, and that will still solve. So this is one of the fundamental notions of a linear solution. To me, the key point to emphasize to students here is that you, again, want to reduce something to a small, simple problem and build up from the simple problem. I start off with some basic solutions, and I build up from that. If you start talking about vector spaces, this is more at the college level of linear algebra, you can almost think of different directions. As a Bostonian, I hate saying good things about New York, but I've already broken to you from the last class, what's the one thing about New York City that I like? The grid system in Manhattan, the east-west, north-south, is much better than what's going on here. Which is one of the reasons why I want to get out of here before the snow hits, because this is already a bad place to drive in. You have 2 simple directions, and you can add them together, and you can represent any solution in some sense in terms of those 2. The fact that we have 2 free parameters here is coming from the fact that this is the depth 2, is that once I specify 2 values, all the other values are determined. So what I want to do now is I want to try to guess what the solution should be. And this is where the method of divine inspiration comes in. So I'm going to guess something. I'm going to guess an is equal to some number r to the nth power. So this is, in some sense, where the divine inspiration comes. But remember, this is a cohesive set of lectures. So when you're filling out the value, cohesive, well thought out, well prepared, not being done on the fly at all, as my college students complain all the time. What was the very first thing we did when we looked at the Fibonacci numbers after we wrote them down? We bounded them. We saw they grew at least as fast as root 2 to the n. They grew no faster than 2 to the n. Highly suggestive that there's some growth rate, called r, such that they grow at the rate of r to the n. We know it's growing geometrically. Now, there could be other terms. It could be, unfortunately, maybe it's r to the n, natural log of r, something like that, which would be a nightmare. Maybe you even have like a 1 plus e to the minus. You could have some ghastly something like that. Hopefully, that's not going to be the case. But from what we saw before, it's not a bad idea to just guess maybe an equals r to the n. It's consistent with what we saw. So consistent with root 2 to the n was less than equal to fn was less than or equal to 2 to the n. So now let's assume it does equal r to the n. If it equals r to the n, then we would get r to the n is r to the n minus 1 plus r to the n minus 2. Bring everything over and subtract. We get r to the n minus 2, r squared minus r minus 1 equals 0. So we get either r equals 0, or what do we use to solve this? Quadratic formula. 1 plus or minus the square root of 5 over 2. Now, if I take r equals 0, every single term is 0. That's a solution. It's a boring solution. We would probably give it the official name, the trivial solution. The real solutions are the 1 plus and minus root 5 over 2. And from what we saw before, this leads to the general solution. Try something Cn of the form a times 1 plus root 5 over 2 to the n plus b 1 minus root 5 over 2 to the n. And now that's looking a lot like this. We have the correct growth rates here. And now we just choose, n equals 0 and n equals 1 to get a and b. And that's how you would prove Binet's formula. And again, what's so miraculous about Binet's formula is this allows us to jump to any term in the series without going through all the previous terms. From a computational perspective, this is huge. This is the 21st century now. Everything's fast-paced. In terms of what really matters, we need to be able to do things quickly. There's so much data coming in. There's so much computation that needs to be done. We need fast ways to do this. And this allows us to calculate things extremely rapidly. So this is why this is one of my favorite formulas in all of mathematics. Okay? So what I thought I would do now is shift and talk about two different examples of where Fibonacci numbers, I'm sorry? I thought I would talk about two different situations where the Fibonacci numbers are used.
I'm just curious,
Yes.
how old is this formula? When you said it's so important now because everything comes so fast and information comes so quickly, Binet's formula
Right.
solves that problem.
The-
How long do we have access to this as opposed to having to go back through and check every other number?
That's an outstanding question. I don't know. I should know. That's it. Yeah. That's a great thing as to did Leonardo know this? So hopefully, okay, good. So Mark's already doing the Googling to see how long it's been. Yeah.
So when you were in college, say, did you know?
Oh yeah. This is classic. It's at least 50 years old. And so this has been known for a long time. I'm sorry? 1840, yeah. So this is a great way to prove a lot of identities about Fibonacci numbers. And in fact, one of the ways you can prove things using this identity is brute force. It's extremely painful to use this, but it is a way to attack a lot of these problems. Okay, so let me give you two examples of how Fibonacci numbers can be used. I'll do one example in detail and then just talk a little bit about how you can generalize it to be a little bit more useful and interesting. So we could be trying to calculate, how many rabbits are alive at a given time, and let's say this represents how many rabbits you have. And so there's a couple of things that could be a little bit ridiculous in here. Do rabbits ever die? And so how long do we want to do this? So I'll do I'll do a whale version. Any Star Trek fans? Okay, Star Trek 4: The Voyage Home. What were the names of the two whales?
Google it.
No, they are a couple. They're a very famous comedy couple.
Oh,
Gracie and George, yes, Gracie and George. So let's imagine we have whales, and then whales live to be how old? 4, and then they die. They live to be 4, and then they die. They live till 4, and then they die. Yes, let them die quickly. Well, if I do 50 years, the calculation is going to become a lot more involved. And so let's assume the whales die after 4. Okay?
Bi-weekly whales, then, if we want to have a short life.
Because I like Star Trek. I like Star Trek. And so let's let AN be whales 0 years old. BN will be whales 1 year old, ... DN will be whales 3 years old. Die at 4. Now again, this is a very simplified model for real life. All right? We will assume that when you're born, you're not having calves, you're not having new whales. We'll assume that when you are 1 year old, you have 2 pairs. So have 2 pairs at 1, have 1 pair at 2, enjoy life at 3 in peace, and then die at 4. So we can model how the whale population grows. So if we let Vn be the vector An, Bn, Cn, Dn, we can relate how many whales we have of each group at time n plus 1 to how many we had at time n. So if I want to know how many whales are born in year n plus 1, well, however many whales I had 1 year earlier who were, sorry, 2 pairs. So I mean,
Very complicated. You need a whole table.
Because the 0 ones turn 1 and then the 2.
so I think it should be something like this. So over here,
Okay.
the whales that were 1 year old here, they're going to get pregnant, and then they will give birth 1 year later. The whales that were 0 years, 1 year, 2 years old have 1 pair that gives birth. These people are just enjoying life. How many whales do I have in year n plus 1 that are 1 year old? In terms of how many whales I had the previous stage, what would it be? It's just a sub n. It's 1 a sub n plus 0 bn plus 0 cn plus 0 dn. How many whales do I have who are 2 years old? It's 0 an plus 1 bn plus 0 cn plus 1 dn. How many whales do I have who are, it's going to be 0 an plus 0 bn plus 1 cn plus 0 dn.
Why do you have 1 dn in the...
Because I can't write.
Did you go with matrices last time?
I'm sorry?
Did we see this a little bit in the context of matrices?
You can easily see this in terms of the context of matrices. And in fact, we can write this as Vn plus 1 is the matrix 0, 2, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0 times Vn. So it's a Markov chain, and you can use this by calculating high powers of the matrix to see how things evolve. It turns out this is a difference equation. Again, I don't want to go into too much detail right now. I want to do enough detail so that you can see what's going on. If you want me to provide more, I'm happy to provide notes. I've got a lot of notes on using this. You could add all of this up, and you can clearly see that you'll have relations between previous times. And this will just tell you how things evolve. Now, what do you think is a little bit unrealistic about this model of whaledom?
There's nets, there's hunters.
There's nets, there's hunters, there's diseases, right? The fact that everybody dies at the same time, everybody always has 2 calves at this age,
Always get pregnant.
right? Sometimes it just doesn't work. So in a situation like this, you'd want to replace these numbers with random variables. And so now you could ask, well, what if I have, say, an average birth rate, and I have some kind of control of fluctuations? How might I expect the population to behave? And you can now start playing these stochastic games. And rather than using a completely deterministic system, you can use a variable system. Again, in this deterministic case, it's very easy. I just need a high power of this. There are ways to use this method of divine inspiration to write down what the solution should be. I'm just trying to give you some sense of how the Fibonacci numbers can be used. Okay, so the Fibonacci numbers would be a very simple case. For the Fibonacci numbers, we would have, let's say now we have Wn is the vector fn minus 1. So if I now have fn plus 1 fn plus 1 is fn plus fn minus 1. Fn is fn plus 0 fn minus 1. So this would be 1, 1, 1, 0, acting on the vector fn, fn minus 1. And so this would give us the vector wn plus 1 is this matrix 1, 1, 1, 0, calling it wn. So I can write down the Fibonacci numbers by using a matrix equation. And then understanding powers of this matrix gives me very nice ways to calculate what's going on with the Fibonacci numbers. Now what you'll see here is I need ways to multiply huge powers of matrices quickly. That will come up in our last unit. And so if we'd done it the other way, then it would have been an application of the Fibonacci numbers. But this idea of if we want to see how things go, well, we can just iterate. So this is the same. Let's see. This not enough real estate. So I will kill the text in the middle.
So now that you've released that, can I ask?
Sure. Now that it's gone, yes.
What does it mean there are 2 pairs at 1 and 1 pair at 2?
Oh, just that when the wheels are 1 year old, they get pregnant and they give birth to 2 complete pairs of wheels. So right now, I'm letting these represent a number of pairs. So they have 4 baby wheels.
Wait, 1 pair of wheels has 4 baby
No,
wheels?
1 pair of wheels has 2. Right now, these should really represent pairs of wheels.
Oh, okay.
I mean, otherwise you have to divide by 2. You have to then worry about, what if the balance is not right and you have these poor, or how they come, don't want to get into those issues beyond my pay grade.
So in the second year, each pair.
So each pair of wheels gives birth to 1 new pair of wheels. And in the first year, each pair of wheels gets pregnant and gives birth to 2 pairs of wheels the next year. Sure. So AN represents the number of pairs of wheels that were just born. BN is the number of pairs of wheels that are 1 year old. CN is the number of pairs of wheels.
Okay, it's not per. Okay.
It's not per. And so here, each pair of wheels gives rise to 2 new pairs the next year.
It's not how many. Okay.
Right.
So when you're saying have 1 pair at 2,
Exactly.
this means
Each pair of wheels generates 2 new pairs.
yes, so that's backwards.
I'm sure it's 3 in total.
So you get 3 new pairs. Well, it's 3 if BN and CN are the same.
So are you saying we have fewer babies as they get older?
Yeah.
Oh, all right.
That part was at least reasonable. If nothing else was reasonable, at least that part was reasonable.
And they enjoy life the last year.
They watch all the grandkids and great-grandkids. They work with Aquaman to have these little, pens to contain them.
You can't do anything about them dying in 4.
No, well, you could, of course, make the model more complicated and allow wheels to... And then you'd probably have a couple of years where they're not having kids. And then there would be some probability of them dying and you're not advancing. And then there's a lot of, really good math bio stuff you can get into in terms of, the harness rates.
So then you would multiply, like if you then introduced foxes or wolves, then you'd have another.
You would have another
predator
term.
matrix.
Yes,
You could
and
multiply that one by
exactly. And then for the predator, the more predators you have, the more deaths you would have. And there would probably be a product term. So usually these models have a product of number of rabbits and the number of foxes in terms of trying to estimate how likely is it for a fox to meet up with a rabbit. So there's a lot of great stuff you can get into if you're trying to do like a math bio unit. This is a wonderful segue into math bio. Going to the...
Connecting,
Yes.
just the first beginning of the Fibonacci
Yes.
sequence, that's relating to the total number of whales at any...
Well, this wouldn't quite be the whales because the whales had a
I'm
longer...
talking about just the numbers, not the FN.
This one's over here?
1, 2, 3, 5.
Well, that wouldn't be the whales.
That's...
That would be a different sequence given by this matrix, by the matrix 1, 1, 1, 0. And the initial condition 0, 1, that would give rise to the Fibonacci numbers. If I wanted to look at how many whales do I have at a given time, I would have to add up all these numbers. And then that would tell me how many whales I have in year n plus 1. And then it turns out that the evolution of that is coming from this matrix. And so if I want to look at the Fibonacci numbers, we just showed Wn plus 1 was this matrix A times Wn, where A is the matrix 1, 1, 1, 0. Well, we know Wn is A Wn minus 1, so if we combine these, that gives us Wn plus 1 is A times Wn minus 1. That's A squared wn minus 1. And then you could continue and get wn plus 1 is a cubed wn minus 2. And you can go all the way down to wn plus 1. This adds up to n plus 1. This adds up to n plus 1. It'll be a to the n w1. So if you know your initial numbers, your two first Fibonacci numbers, f1 and f0, this gives you fn plus 1 and fn by taking a high power of this matrix. So if I want to figure out jumping ahead in the sequence, one way to do this is to use some techniques from linear algebra. That's a little bit far afield. I just want to show you how we can relate this to different things. If you have students who are studying matrices, here's a nice application of matrices. If you can compute high powers of this matrix well, and this is where there's something called eigenvalues and eigenvectors that allows you to do these calculations very quickly, very nicely. And you can jump to solutions. You can write down something very similar to Benet's formula. If you don't know this, this is a very nice way to codify how you do the computations and just see how things evolve. So this is one application of difference equations. The application is to model how systems evolve. One great one is how populations evolve. And you can set this up and you can put this in a framework where we can use things like the Fibonacci numbers to solve this. The difficulty is having a reasonable model. This is not reasonable. This is being recorded. I can't use the proper phrasing, but this is not an accurate model for how whales would evolve. But it's mathematically tractable. And so we often start off with something like this, and then we start playing games and say, well, if I replace these with random numbers, what do you think will happen? And how much of a variance here, how will that affect things as we go on? When the financial crisis hit, we had faculty meetings at Williams. Each meeting of the faculty, the best case scenario from the previous meeting was now the worst case scenario as things kept going further and further south. And one of the things that I found a little bit implausible in these meetings is they were always saying, we will assume the market is going to have this many years at this return rate and then this many years at exactly this return rate. Well, okay, sure, that's maybe what you expect, but let's look at some fluctuations. You expect the rate will be -3. What if we get a -5 in the very beginning and then one of the 8s later becomes a 10? On average accounts, it adds up to the same thing, but the order in which these things happen, how bad is our exposure? And so this idea of looking at matrices and flipping things is very nice. The next application I thought I would talk about was roulette double plus 1. How many of you know how roulette is played? Okay. We're going to do a simplified version of roulette. And so in this version, is it two L's or 1 L? 2 L's? Okay. So I can't even do the simplified version because in roulette you have, I think, 18 reds, 18 blacks, and 2 greens. I don't have a green marker. I don't even have a black marker. I at least have a blue. So the blue kind of looks like black. So we're going to just help you out and pretend that there's no green. Vegas is not willing to give you this advantage. I know, this is huge. Okay? So the way the simplified betting works is you bet $1 on red. If red comes up, you win $1. If black comes up, you lose. What I like is I am smart enough, I know too much math to actually play roulette, but I've seen what Vegas has now done. I've seen airports in Las Vegas. And what they do is now when you win, you no longer get your money. You get an electronic credit on the machine so that you're more likely to keep playing until the credits are gone. Another thing which they do is they now display the results of the last couple of spins. And there's 2 types of morons in the world. There's the type of moron who goes, oh, red's come up 5 times in a row. Red is lucky. I'm going to bet on red. And then there's the other type of morons. Oh, black is due. Got to bet on black. And they really don't care which type of moron you are, as long as you're the type of moron who's willing to bet money. If you're that type of moron, they're happy. And so now, how does this evolve? Well, let's take one of the most famous strategies. It's called double plus 1. So you bet $1 on red. If you win, you net $1. Oh, sorry, net $1. If you lose, what happens? You lose $1. So down $1, bet $2.
To get caught up.
If win, what happens? So where are we? So I bet $1 on red. If it comes up red and I win, I plus $1.
Net $1.
If I lose, I'm down $1. I bet $2. If I win, I now get $2 back.
Net $1.
And I net $1. I was -1 plus 2 is +1. So we net $1. If lose, how much are we down? 3. So we bet how much? 4. If win, how much? If win, we net. If lose, we're down 7. So what do? We bet 8. So this is called double plus 1.
So the best you can do is net $1.
But then add lather, rinse, repeat.
Shower all day.
As a mathematician, shower all day is just not right. Okay. So eventually you win $1. So all you have to do is you keep doing this and you net $1. Then you repeat and you net another $1. Then you repeat and you net another $1.
So subject to unlimited resources.
So that's one issue. Okay, so one issue is unlimited
Didn't take very long to get to 8.
resources. There is a solution. So the eccentric rich uncle hypothesis or the eccentric rich uncle aunt hypothesis. So you have a family member who has unlimited financial resources and a willingness to stake you in any bet no matter what. Now this uncle, in addition to being rich, is also very eccentric. If you ask your uncle for $1, the uncle says no. You know, my infinitely valued portfolio is not enough for me to spare you $1. But I will cover any bet you need covered. All right. So this eliminates the issues of having, finite amount of resources. You have the uncle who will stake you.
You need bus money, you can sit there and they will stake you.
I'm sorry?
You need bus money, they'll stake you.
They'll stake you.
Get your
So you can keep betting. Why am I not in Vegas using this now?
2 greens.
Doesn't matter. Even with the 2 greens, it just takes longer. 2 greens only slows me down. What's the issue?
You waste all day just to get it.
Hire a high school kid. Hire a high school kid. There was a Canadian scratch lottery where a Canadian statistician, geologist had figured out that they were not randomly putting the numbers down, and he cracked the pattern. And when he told the Canadian lottery, they said, they didn't believe him. So he sent them 20 tickets and he told them how to scratch. And he was right 19 out of 20 times, at which point they listened. And he said, look, I calculated it. I make more money in my job than I would make scratching tickets. I would have talked to high school kids. And just, because for the high school kids, it would be a really good after-school activity. But don't worry about the fact that it's only $1. We can multiply this and say we're making $1,000. Why am I not at Vegas using this? And you need to know a little bit about how Vegas works, or about the New England Patriots. And I'm a Patriots fan. It pains me to make these jokes. What do we all know far more about as Patriot fans than we knew, say, 2 weeks ago? Air pressure. What can you tell me about air pressure in a regulation football? It's going to be at least 12.5 psi, and?
It's going to go down when it's cold.
Well, it's going to go down when it's cold. Well, what else? It's at least 12.5. No, it's at least 12.5 and? Less than 13.5. 13.5. Now, Aaron Rodgers has admitted to liking to overinflate his balls. So, footballs. I don't know if he said, I think he just, I'll have to check the transcript. And so, it's not clear exactly how widespread this is in the NFL, but there's a minimum and a maximum allowable pressure. Vegas has minimum and maximum bets. So the problem is you might be at the point where you have to put down $32 trillion. And your rich uncle says, sure, no problem, and just signs a check and gives it to you. Vegas doesn't have to take the bet. And so Vegas has a house limit. And so what happens is when you win small. And when you lose big. And when you lose, let's say we're now down $31, but the maximum we can bet is 20. We can't put down a big enough bet. And that's where Vegas wins.
They'll comp you a room.
Oh, they'll comp you a room. No, without a problem. But that's why Vegas can win in something like this. And that's why so many people try this strategy.
Because they cut you off before.
They cut you off before. Oh, yeah. So they calculate, and I'll show you how to do the calculation of what is the probability of getting a certain number of blacks in a row and going bust if you're betting on red. The probability is much higher than you would expect. I think you have over an 80% chance of getting 5 consecutive blacks in 100 spins. It's much higher than you would expect. People are terrible at randomness, in terms of how many, if I flip a fair coin, how many heads and tails should I have? It should be about 50-50. But strings of heads, strings of tails, that's a lot harder for people to know. And it turns out the same math that solves the Fibonacci numbers solves this and explains why Vegas is able to stay in business so well. As an aside, one of my former students was telling me that he had a friend a couple of years ago who placed a bet on the Patriots to go undefeated and win the Super Bowl. And this is the year where the Giants came back against us with that miraculous catch. In the third quarter, Vegas calls him up and offers to buy back the bet. So he had bet $500 on the Patriots at 1,000 to 1. So the bet was 500 at 1,000 to 1.
Wow.
And Vegas offered 300 to 1. And my friend's friend said no. And so when my friend told me the story a few days ago, I told him, your friend is a moron. Not because he didn't take the bet, but before the game began, he should have bet on the New York Giants. If he puts $10,000 on the Giants before the game goes, the Patriots were predicted, the Vegas line was Pats by 14. You put $10,000 on the Giants, and then you basically minimize your risk. So if the Giants win, you make a killing from that $10,000 bet. If the Giants lose, oh no, instead of getting $500,000, I only get $490,000. And so, you could cover your risk. And so this is now one of my favorite stories to tell. The non-painful one was another student's uncle was in Vegas, and he woke up the next morning from a really bad drinking spree. And he found that he'd placed a $1,000 bet on the Patriots to win the Super Bowl. And what amazes me is that he was actually somehow able to save the stub. And it was the year we beat the Rams. And so he made out, I think he got $300,000 from that. So what I want to do now is I want to show you how you can use Fibonacci math to solve this problem. And I have a really nice 6-minute video that goes through all the calculations in detail. So let's let AN be the probability do get 5 black, well, let's do not get 5 blacks in n tosses or spins. And let's let Bn be the probability we do get 5 blacks in n spins. Consecutive, thank you. That's very important. In n spins. What can you tell me about AN and BN? What relationship must they satisfy? So we know AN plus BN equals 1. So if I can figure out AN, I know BN. If I can figure out BN, I know AN. One of them is easier to find than the other. It turns out AN is the easier one to get. So finding the probability I do not get 5 blacks is easier than the probability I do get 5 blacks. So I will calculate AN, and then I will leave the calculation of getting BN as an exercise. So here is my start. And I want to calculate AN. I have 2 possibilities. I will assume for now that each possibility happens with probability 1/2. In the real world, Vegas gives itself the 2 greens. The probability is a little bit less than 1/2. Doesn't matter, it just makes the algebra a little bit worse. So half the time I get a black, half the time I get a red. I want to calculate the probability I do not get 5 consecutive blacks in n tosses, given that the first tosses are red, what would that probability be? This is the hardest part of the whole analysis.
You can't, because you just break the probability you're not getting.
Then I'm not going to get 5 consecutive blacks anywhere in n tosses, given that my first tosses are red. This is the hardest step of the whole analysis.
We'll have a bunch more.
I have n minus 1 tosses to go. It's a n minus 1. Because my first toss was a red, it can't start off a string of 5 consecutive blacks. Now I look over here, and I've got black, red, half, half. What's the probability I don't have 5 consecutive blacks, given that I start black, red? A n minus 2. All right, so now I split again. Black, red, a half, a half. What's the probability I don't have 5 consecutive blacks, given that I start off black, black, red? A n minus 3. All right, let's do it again. 1 half, black, red. What's the probability I don't have 5 consecutive blacks, given that I'm black, 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 red? A n minus 4. All right, let's split it again. All right, 1 half, black, red. What's the probability I don't have 5 consecutive blacks, given that it's black, 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 red? A n minus 5. And this is where I now make the joke, damn it, I shouldn't have done something like this. I'm running out of board space.
You win on the other side.
Right, now you can answer. And now we're at 0. Why is it 0? I've got 5 consecutive blacks. What's the probability you don't have 5 consecutive blacks, given that the first 5 spins are black? This is close to the easiest possible probability question I can ask you. And so we get the following recurrence relation. We get an is 1 half an minus 1 plus 1/4 an minus 2 plus 1/8 an minus 3 plus 1/16 an minus 4 plus 1/32 an minus 5. It turns out you can solve this with a version of Binet's formula. I'm not going to go through and do that, but you could use some kind of version of Binet's formula. It's a little bit harder because I have more terms. Rather than using the quadratic, I have to use a quintic, a little bit more painful. But I can calculate a couple of these values. Can somebody tell me what A0 is? The probability I do not have 5 consecutive blacks, given that I spin 0 times. What's A1? A2? A3? A4?